Wavefunction was used a century ago for light, radio, and mechanical waves when Schrödinger made its own version. He was describing particles and atoms in ondulatory form using the wavefunction. The general form of Schrödinger's equation has an imaginary unit. This value has no physical meaning. I is a math invention. Nobody knows what or why, and even Schrödinger was perplexed on how this makes the equation work. Anyway, Schrödinger's waves are different. On one side of the equation there is momentum and potential energy. On the other we have an imaginary component, and this is where quantum kicks in. Schrödinger's equation describes an ondulatory behavior. Interaction is not conceived. It's quantum physics to theorize the collapse of the wave function in one point as the interaction. In quantum mechanics, the system is spread as wave function. The wave function completely describes the system and contains all the properties we want to analyze: mass, spin, momentum, and so. Here we have all possible states for the system, potentially infinite. So the system is everywhere and nowhere, and it is undefined until collapse. How and where the collapse is more likely is defined by the amplitude, the probability distribution in finding the system, and by many points it looks very like the classical amplitude on waves. Collapse is a quantum mechanics event. Every time it's done by hand, it usually matches detection. So in quantum mechanics we can teleport energy because the system, spread all over, flows into one point. Now this causes issues as the measurement problem. The amplitude is a probability of detection, but the collapse has no physical explanation or mechanic, because you can't rule this arbitrariness. Until collapse, the system is spread over the wave function. It's everywhere and nowhere, so it doesn't interact with matter. It's a complex value because of the imaginary. So according to quantum mechanics, the wave function lies in something like a parallel universe. And that's why it should tunnel through matter. A side question should be, if the system can't interact with the material world, how it can interact to collapse? Anyway, collapse is when and where the wave function interacts, and the whole wave instantly disappears, emerging into the point. And it does it no matter the distance. Even if part of the wave function is now in Andromeda Galaxy, the collapse on Earth will immediately affect that part far away too, dramatically violating relativity. This because quantum mechanics requires that each system is spread over the entire wave function and gives only one outcome. Otherwise we are in classical physics. The measurement problem also emerges in another way. The wave function connects the emitter with the receiver where it collapses, but there can be many obstacles in between. If we put a small slit here, the experimental results in the receiver changes, showing that the slit affects the result. Quantum mechanics deal with this, making the wave function interact with the slit and then collapse in the detector. So the wave function interacts and changes without collapsing, contradicting its own rules. The collapse is still triggered at the detector, and we have agreement with experimental results. There is no reason for the two interactions to be different, but this is quantum mechanics having measurement, observation, weak and strong as types of interaction that should always mean the same, yet they can be used by quantum mechanics in different ways. Beside the ambiguities, we see collapse is a very specific quantum effect. So one interaction is very different from the other without an actual reason. And this special action, with very important consequences, is done by hand. Also, there is no implicit randomness in the wave function, because randomness comes with the measurement process. Differences between interactions have no clear boundaries, So the measurement problem in quantum mechanics originates from the poor definition of measurement in quantum mechanics. It's self-made. We have example with interferometry. A light pulse is detected in the receiver, but the emitter is separated by a beam splitter that divides the wave, and mirrors reflect the light again to a second beam splitter. Here pulses on path 1 and 2 meet before being detected by the receiver. According to quantum mechanics, the initial wave function is split along the two paths, but the one system that will appear with the collapse is and is not on both paths. In the interferometer, the initial wave function is the same that reached the detector, so neither the beam splitter nor the mirrors can collapse the wave, even if their interaction is undeniable. The wave function is an undefined single entity even when it's spread, so we have unexplainable different and local interaction on each part of the wave. And even more, these do not cause collapse. And if I experimentally detect light here, there is no number of type of interaction that can stop the wave function. Quantum mechanics can teleport, split, tunnel, and at least part of the probabilities goes here, so that the entire system can collapse. When I add a receiver here which steals all previous detection, the wave function still agree with experimental results and will be collapsed here. Another point is interesting in interferometers. The beam splitter always separates the incoming light, and the second splitter has two beams incoming. If we place a second receiver on this side, we have no detection until path 1 is blocked. Now receiver 2 also start clicking, and we are blocking path 1 using a third detector. We have detection in 2 only when nothing is coming from path 1. So even if detector 3 doesn't click and the wave function could tunnel, this part must be blocked in order to detect something here. Here we notice that detector can mislead the interpretation, because they can miss an important part of the energy and return an incomplete picture of the wave. The same happens with slit experiments, and adding a second opening, we are changing even more the outcome, but collapse of the wave function is still at the detector. So wave function can also change with local, partial, and different interactions without collapse. These interferometry results are not surprising for classical optics, but are useful to show quantum mechanics. At each execution, light can give multiple detections, while the wave function is tied to a single outcome, one photon without amplitude. Another important case is the famous alpha particle in cloud chamber. Here we can observe a suspiciously deterministic straight line that quantum mechanics try to explain grasping at straws. The spherical wave function becomes a ray that can make its way through matter without collapse. So the wave function can also be a ray without collapse. The wave function shouldn't interact with the environment until collapse, yet there are many experiments showing how the system can continuously interact while being in a parallel universe. The system is undefined and non-local. What is interacting? Only a determinate state, even when unknown, can accumulate delay, because there is an actual value to modify. While unknown is hidden variable, undefined is quantum mechanics, and they imply two very different concepts. At this point, we have a lot of ambiguous and contradicting rules that need to be arbitrarily applied. Collapse is just one of them, as measurement is just one piece of the problem. Emission and detection are facts. Unknown events in between are described with unphysical mechanics and are still inferred. Thanks to the wave function and the measurement problem, quantum mechanics can do all kinds of teleport, and with the final collapse still matching the experimental results. All the appear and disappear violate energy conservation and relativity. Yet, all of this is part of how we deal with physics at a quantum level. and quantum mechanics heavily depends on the wave function because it's used everywhere. These topics are debated since decades, but in the end it's all effects that matter. The logical order requires that only when an effect occurs it is worthy of acknowledgement and analysis. Quantum mechanics instead invent effects to give meaning at mass solution, but there is no proof quantum is the behavior of fundamental physics. We can't see them in experiment, and they are still valid today only thanks to consensus. Quantum mechanics uses its model to define reality of events. It should be the other way around, but this is how you make quantum effects true. Unfortunately, agreement and lack of proof are not proof. Quantum effects makes no difference, so they don't deserve acknowledgement. In the meantime, known physics is repeatedly violated by quantum mechanics, while all outcomes remain within determinism. When the wave function collapses in one point, we see one aspect of the wave-particle duality. According to quantum mechanics, photons don't go anywhere. They spread as wave function and emerge as particle with the collapse. But photon is the result of collapse. So what's the purpose for this? The interaction already happened and it's a particle, it can't go anywhere. So photon has no use, it's just the name for light interacting with particles. Even two photons entangled is just short for two-wave function having some correlation. Indeed, in our experiment we don't emit photons. Quantum mechanics says our laser shot wave functions, each one representing a single photon. It is often stated that quantum mechanics can make astonishing predictions. So let's try something simple. The sun emits each second a tremendous amount of energy. Can quantum mechanics take an emission here and tell us where it's going? As example, will photon here hit a planet, or will they go outside the solar system? Quantum mechanics can't tell because it needs the answer to give the solution. We have to do this. Light emitted by the sun is detected here on Earth. Determinism will tell you wave propagated C. After 4 minutes, light is halfway for sure. Probability is 100%. Quantum mechanics, on the other hand, can only look at the wave function collapsed here on Earth when the event happens. 4 minutes after the emission, the photon still doesn't exist. The system is undefined everywhere and nowhere according to wave function probabilities, and this keeps going for all 8 minutes until the random collapse. It seems that predictions of quantum mechanics are of some very specific kind. Quantum physics needs the outcome to give the solution because it's a theory but observable. While classically systems propagate from A following some path, quantum mechanics only deal with cases we did know the results and connects A and B through a wave function. Thanks to this, the math solution can agree with experimental outcomes even lacking a physical cause. So agreement can be unjustified, and we can also witness retrocausality until mass checks. Curiously, quantum mechanics can spread and teleport waves all over the universe, but experimental outcomes always matches the behavior of deterministic waves.